Well, today let's move on to the next stage of our discussion. Right. So in the last class, we were discussing about the uncertainty principle. So today let's discuss the Schrodinger's equation. What is the significance of Schrodinger's equation, or what do we get from this Schrodinger's equation? See, we all this while we are speaking that there are waves, particle waves, or particles behaves like waves. That means a moving particle is always associated with a wave, which describes the wave nature of that moving particle. Right? If I say there is a wave associated with a moving particle, or a moving particle behaves like a wave, that means I should something to define that the wave nature of that moving particle. So for that, I need a wave equation. So that wave equation is particular to that that particle, and it should be in a position to define the nature of the particle, because moving particle has location, that is position, it has momentum, it has energy. So all these things we should be in a position to evaluate from the wave equation. Now, how to get the wave equation? We already know. Suppose if there is a wave which is moving, if there is a wave, right? If there is a wave, sinusoidal waves, we know. If there is a wave, generally we call it. This is a general wave equation. Y is equal to A sine or cos, okay, omega t minus kx, or there are different forms. This is one of the forms. You also have e to the power of, okay, that also is there, I omega t minus kx. There are different forms to define a wave. Okay, so this is for waves which we know, electromagnetic waves or sound waves, we can define like this. Here from this we can get its location, we can get its wave number, we can get its energy, we can get its what is this, angular frequency, all right. But the wave what we are talking is a wave which is associated with the particle. Particle is in motion, so there is a wave associated with the particle. Now, how to get this wave equation? Right? This is a general wave equation for waves what we know till date. But this is a different kind of wave where we say a particle is there, particle is moving, and when the particle is moving, one of its properties is varying like a wave, and we have to find what is the equation for this wave, right? So for that, how to start with? We don't have any information, right? So this is called as Schrodinger's wave equation. And where we have to start? We have to start from define a particle, right? Define a particle. Let's say a wave traveling along x-axis with frequency nu, wavelength lambda, and velocity v. So that omega equal to 2 pi nu and k is equal to 2 pi lambda. Because we have to define a wave, let's start with a basic wave. Right? So write down this Schrodinger's equation. Schrodinger's equation, and note down this center statement. Did you note down the statement? So a general typical wave equation for this wave is y equal to a e to the power of minus I omega t minus kx. Right? Y is equal to a into e to the power of minus I omega t minus kx. This is a typical wave equation for this wave. Okay. Here, y is the displacement of the wave along y-axis. Of course, it is moving along x-axis. It is a transverse wave. A is the amplitude, maximum amplitude. Omega is the angular frequency. T is the time, at any time, whatever the time we consider. And K is the propagation constant. X is the location or the distance. Now, we know that from the quantum theory, we know that energy of wave is E is equal to h nu. When we bring in the concept of photon, so we know that energy of the wave is given by E is equal to h nu. From the quantum theory. Okay. When we know E is equal to h nu as per quantum theory, we know that nu is equal to E by h. Just rearranged. Nu is equal to E by h. And we have omega is equal to 2 pi nu, which is equal to 2 pi E by h, which is equal to E by h cross. Note down this. Which is E by h cross.
Excuse me,
Okay.
sir.
Yes.
So what is A in that equation?
A is the amplitude of the wave.
E?
A is the amplitude of the wave.
Sir, E?
E.
Ah.
E is exponential factor. It's a function, right? Just like sine function, E is the exponential function. That's it.
Okay, sir. Thank you.
Sir,
Yes.
omega is equal to 2 pi E by h. How did it become E by h, sir? Means where did a 2 pi gone?
2 pi is below h cross. H by 2 pi is h cross.
Okay, sir.
Okay. Next. Similarly, P is equal to h by lambda. This also we have got from the, what is that? De Broglie equation, De Broglie hypothesis. P is equal to h by lambda for a moving particle, right? Do you remember? Momentum of a moving particle is equal to h by lambda. Therefore, 1 by lambda is equal to h by p. Therefore, k is equal to 2 by lambda or p by 2 by lambda.
So,
It should be here.
lambda is p by h.
Sorry.
1 by lambda is p by h. No,
Yes.
so.
So, okay. Wait. Here it should be h. No, k is equal to 2 pi lambda is sorry. Right, that's right. K equal to 2 pi by lambda. Okay, then you substitute 2 pi by lambda is equal to h by p. P will go up. Wait, just a minute. I'll rewrite.
Not that statement, so the previous one.
This one.
This is
Yes,
1 by
sir.
lambda should
1
be
by
by
lambda
h, no,
equal
sir.
to- Okay. Oh, sorry. Rewrite this. Interchange these two. Sorry. Interchange these two. Then your k is 2 pi by lambda. Substitute for lambda. Substitute for 1 by lambda. For 1 by lambda, we have p by h cross. Sorry, p by h. Of course, 2 pi goes below h and it becomes h cross. So K is equal to P by H cross. Omega equal to E by H cross, K is equal to P by H cross.
Sir, what is the K, sir?
K is propagation constant of a wave or wave number, which we call as, it is called as wave number or propagation constant of a wave. Now, look here. What is this omega?
Sir, hello, sir.
Yeah.
Sir, if we keep in place of 1 by lambda p by h, we will get 2 pi h. No, sir. How can we write h bars?
No. You have to interchange this. Did you interchange this? 1 by
Yes,
lambda
sir.
is
If
equal
we
to P by H.
interchange only, we will get 2 pi h. No, sir. We won't get 2 pi h by 2 pi. No, 2 pi by h. No, sir.
Wait. P is equal to sorry, forget. 1 by lambda is equal to P by H. Okay. Then we have P is equal to lambda is equal to 2 pi. Instead of this 1 by lambda, you substitute P by H.
Okay, sir. Okay, sir. Understood. Sir.
Right? Now you got.
Sir.
Okay, now listen here carefully. What is omega?
Angle of
Wave number.
Frequency, our wave frequency, angular frequency.
Angular
right?
velocity.
It is called as angular frequency. It is pure characteristic of a wave. Do you agree? Because we have omega equal to 2 pi nu. Nu is frequency of the wave. So omega is pure characteristics of a wave. Do you agree?
yes, sir.
What is K?
Wave number.
Propagation constant of a wave or wave number. Propagation constant of a wave or wave number. So it is pure characteristic of a wave. Do you agree? So omega, a pure characteristic of a wave, K, which is a pure characteristic of wave, have been expressed in terms of E. Of course, E also is a characteristic of E also characterizes wave. Of course, it characterizes wave as well as particle. That is not an issue. But this K, propagation constant, that is connected to P. What is this P? What is P?
KH
P is
cross.
momentum. P is momentum. Yeah, what is this P? P is characteristic of what?
KH.
Come on, think again and tell me. P is characteristic of what?
Particle nature.
Very good. P is characteristic of a particle, moving particle. All this while what we are studying is, we never attached momentum to a wave. We always attach momentum to a particle which has mass. So now we are expressing, we established a relation between K, propagation constant, and momentum. As soon as the momentum comes into picture, we can say whatever this equation represents, if it has a momentum component in it, we can say this equation as well represents a particle. So now we rewrite this equation as, instead of y, now I write it as psi. Psi is a very unique symbol which is used only to indicate the variation of probability. Otherwise, y indicates many things. Y can indicate height of a waterway, Y can indicate the pressure in a medium, Y can also indicate the varying electric and magnetic field strength. But here psi indicates only one thing. What is that? Probability of a particle. And psi is always the wave function of a particle. This has nothing to do with a regular waves. So now we rewrite the above equation as psi is equal to A e to the power of minus psi is there as it is, and P by H cross E by H cross. That H cross is taken out, and in place of omega we have Et minus Px. Is this equation acceptable? Now, what is this equation in represents now?
Excuse me, sir. Can you tell again why in place of omega we took E and K in place of P?
See, using the quantum mechanical concepts, we are expressing omega and K in terms of E and P. Using quantum mechanical concepts, we are expressing omega and K in terms of E and P. As soon as P comes into E also, we have taken from, we could replace omega with E by considering quantum mechanics. That is the photon theory, that light consists of particles, photons. And P, as such, P always indicates a particle, right? P always indicates a particle. Therefore, we have replaced omega and K with E and P. So as soon as the E is obtained by considering particle nature of light, P is as such represents particle. So these two combinedly represent particle nature. These two combinedly represent particles. These two combinedly represent particles. But this equation as such represents what? Wave. Therefore, this equation represents wave of a particle. This equation represents wave of a particle. Do you get it?
Excuse me, sir.
Yes.
Sir, could you please tell that as a point so that we can write it down?
Yes. Note down. Well, after this is done. After this is done. Write down. Omega is represented in terms of E. Omega is represented in terms of E. Sorry, wait. Omega and K are represented in terms of E and P respectively. Omega and K are represented in terms of E and P.
Excuse me, sir, could you please repeat? Your voice is breaking a bit.
Oh. Hello, am I clear now?
Yes.
Omega and K are represented by E and P from the quantum theory, from the concept of quantum theory. From the concept of quantum theory. Okay. Right. Now the wave equation is now the above wave equation. Now the above wave equation can be rewritten. Now the above wave equation can be rewritten as above wave equation can be rewritten as, write down. is equal to psi is equal to a e to the power of minus I by h cross e into t minus p.
Can you repeat the last part, sir, of the equation?
E into t minus p into x. Okay. We got this equation, but this is very general equation, right? Suppose if we have two particles, let's say there is one electron which is orbiting in an orbital, and there is a proton which is moving outside as a free particle. Now, how to put this condition that are how to represent an electron moving in an orbital with the same equation and an electron moving freely outside with the same equation. You know, both of them have energy, both of them have momentum, but this is a very general equation where we cannot attach an orbiting electron and a freely moving proton to this particular equation. This is not possible, right? So for that, we'll have to work a little more and find such a situation that let us find a very general equation, right? A very general equation. In this general equation, you put your conditions. That means an electron revolving in an orbital, you have some certain conditions. It has a potential energy, it has a kinetic energy, you put that condition. And there is a proton which is moving with some speed, it has energy, it has only kinetic energy, put that into that equation. So you should be able to get their respective wave equations just like this. Their respective wave equations just like this, you should be in a position to get. But this is not possible from this equation. So we have to further work out to get one general equation or very general form. We should arrive at a very general form of an equation from which whatever the system we want, whatever the state we want, state of the particle we want, we should be in a position to obtain. Right. So for that, let's work a little more. Next. Differentiate the above equation. You give an equation number to this. What equation number you want? Let's call it as equation 2. We'll call this as equation 1. Okay.
Sir, I have a doubt, sir.
Yes.
Here E is there, no, sir? Is it a total energy or kinetic energy, sir?
Here it is total energy. We are not talking about kinetic energy. It should be total energy. You call this as equation 2. Call this as equation 3. Put the equation numbers, otherwise you will get confused. Okay. Over. So now differentiate equation 4 with respect to x twice. Do it quickly and let me know the answer. Differentiate equation 4 with respect to x twice and let me know the answer. Differentiate this equation twice with respect to x.
Fourth one, sir.
Yeah, equation 4. Differentiate this with respect to x twice. the equation with P square.
Sir,
Yes.
so A P square I square by H cross whole square
I
e
square
power.
you take it as -1.
Okay, so -1 into A P square by H cross whole square e power minus I by H cross into ET minus PX.
You write that A into e to the power of minus I by H cross ET minus PX as psi. It is same as the original psi, right?
Yes, sir.
Yes. Replace and tell me. You will get this equation.
Yes, sir.
X square is equal to
Sir.
minus by H cross square
Got
psi.
it, sir.
Yes, sir. You
Into
get
psi. Yes, sir.
minus P square by
All of
H.
you got?
Yes, sir.
Now differentiate the same equation, that is equation 4 with respect to t. Of course, this we can rewrite as p square psi is equal to minus h cross square dou square psi by dou x square. Differentiate the same equation with respect to t and let me know the answer. Only once. Differentiate only once. What is there to take so much time? Come on, guys.
Sir, minus EI by H cut into
EI by H
psi.
cross into psi.
What is the DI?
So minus
I.
A.
A. No.
I.
That A and all you put as psi. A should not come there.
Okay, minus EI by H cross into psi.
Minus I by H cross. Sorry, EI, capital EI. Right.
Yes, sir.
Fine. Yes. So dou square psi by dou t is equal to minus IE by H cross into psi. This we can rewrite as E psi is equal to minus H cross by I dou psi by dou t. So now we
Sir,
have
it
this
is first equation or which one, sir? That is differentiation of?
equation number 4. Differentiating equation number 4.
I mean, this one, the right side one.
What? I didn't get.
Means at once you have differentiated this one or?
Differentiate equation 4 with respect to x twice. Okay.
This one, sir, right side one.
Right side, differentiate equation 4 with respect to t. This is once, this is twice. Okay. Call them as equation number 5 and 6. Next, what we have, so we know that this equation, this is a general equation, right? E is equal to kinetic energy plus potential energy. E is equal to kinetic energy plus potential energy. Write down. E is equal to kinetic energy plus potential energy. Kinetic energy can be written as P square by 2m, and potential energy can be written as U. U or xt. Of course, if it depends on x and t. It may depend on x and t, or it may depend on only one. It is only x. But let's not bother. It's a function of both position and time. That's all. So E is equal to P square by 2m, which is called kinetic energy, and plus U. Right. Now we have. So now multiply throughout with psi. Next, write down. Multiply throughout with psi. What do we get? E psi is equal to P square psi by 2m plus U psi. Okay. This is equation 7. Substituting 5 and 6 in 7. So write down. Substituting 5 and 6 in 7. What do we get? This is what we get. Substituting 5 and 6 in 7. We get this. I h cross dou psi by dou t is equal to minus h cross square by 2m dou square psi by dou x square plus u psi.
Yes, sir.
Okay.
So are we supposed to learn all these equations?
Yes, you will be asked.
Okay.
Yes. So this is called Schrodinger's time-dependent equation. Schrodinger's time-dependent equation.
Sir, means this all derivations important only, no, sir?
Oh, of course, all. Okay, write down. This is called Schrodinger's. This is Schrodinger's time-dependent equation. This is Schrodinger's time-dependent equation.
Sir, you have substituted 6 in 7 or 5 and 6 both in 7, sir?
5 and 6 in 7. See, P square psi is there. This P square psi I have substituted here. E square psi is here. This I have substituted here. Okay.
Yes, sir.
So this is what we have got. This negative sign doesn't come here, of course, because I has come up. I has come up, that's why there is no negative sign here. Remember that. Multiply and divide by I. So this becomes I square. I square is minus 1. Minus 1 gets cancelled. So I remains in the numerator. That is what is here. Okay. Why did we do this? And what is that we have got now? That is the question. Right? Why did we do this? What is that we have got now? So this is the basic quantum mechanical equation. Just like the Newton's equation, what we have, F equal to ma. This is a very basic principle in the quantum mechanics. This is the basic equation. Right? This is basic equation. Remember, from the first principles of quantum mechanics, what we get is the Schrodinger's equation. So this Schrodinger's equation is a general equation. It could be applied to any system. When I say any system, system means it can be applied to a orbiting electron, it can be applied to an accelerating electron, or it can be applied to a moving proton. It can be applied to any system. It can be applied to hydrogen atom. Anyway, wherever you want, you apply, you start with this equation, right? In this equation, you put the conditions. You put the conditions. When you put the conditions and solve this equation gives you psi. This equation gives you psi. So what the wave function you evaluate out of this equation, this general equation, that is the wave function psi. And this wave function has all the information. Then you have to extract the information from this wave function. This is not a simple thing. First, you have to input all the conditions of the system so that you evaluate psi. Psi would have all the information of the system. Then you extract whatever the information you want from psi. That is the wave function. That is the method. Okay. That's why quantum mechanics is little tedious as well as quite complicated with terms of mathematics. Unless one who is good in mathematics, advanced mathematics, cannot learn well the quantum mechanics. Of course, this is very basic quantum mechanics.
Sir, we should do only partial differentiation only, sir.
Yes. Okay. Next thing. So this is, here we have this psi as position as well as time dependent. That means you see here, this is potential energy. So this potential energy has position as well as momentum dependence. But in many cases, the potential energy would only depend on position. It wouldn't depend on the time. It would be time independent. Momentum would be, not momentum. The potential energy would be time independent, right? It would only depend on the position. In that case, our equation changes, right? In the previous slide, here we have taken, look here. Here we have taken the equation to be time dependent as well as position dependent. But if the potential energy is only position dependent, such as an electron revolving around a nucleus, when it is in first orbit, second orbit, third orbit, depending on that, its energy changes. It doesn't depend on the time, right? Do you agree? An electron in the first orbit of the hydrogen atom, it has minus 13.6 electron volt. In the second orbital, it has 6.8 electron volt. In the third orbital, it has some 3.6 electron volt. So here, it only the energy of the electron is decided only on the position of the electron, whether it is in the first orbital, second orbital, or third orbital. It is not on the time. Do you agree? So in that case, this equation, wave function, need not have the time dependent factor, or the wave function will only be position dependent, or we can even call it as the wave function or the particle is time independent. So based on that, we will have to derive one more equation, which is mostly used in all the cases. It is called as time independent Schrodinger's equation, or Schrodinger's equation in steady state. Write down Schrodinger's equation in steady state. In the bracket, you write down time independent. Schrodinger's equation in steady state. In the bracket, you write down time independent. Why are we deriving time independent Schrodinger's equation? Anybody?
We use it mostly in based on position. Not
The energy, the potential energy explicitly depends only on the position of the particle. So it is time independent. In that case, we don't need time dependent state. Time dependent state. So therefore, we are deriving time independent state. Write down. In many cases, the potential energy of the particle, potential energy of the system, don't write particle, write system. Potential energy of the system implicitly.
Sir, repeat again, sir.
Does not depend on the time explicitly.
Sir, the potential energy of the system
does not depend on the time explicitly. Comma, it depends only on the position. It depends only on the position. Okay. So we have this equation. I is equal to a e to the power of minus I by h cross e into t minus px. This one. So it says time is not a function of the particle's wave function, wave equation.
So what is
Time
written?
is not a
E power minus I by h, sir, or I by h cross?
e to the power of minus I by h cross into et minus px. The same equation, old equation. Okay. So here, this wave function doesn't depend on t. That's what our previous statement says, right? So we will split into, this is time dependent part, this is time independent part. Okay, time dependent part, anyhow, it doesn't affect anything. So this is the varying value or varying function in this whole equation. So let us split it into two parts. Okay, a e to the power of minus I e divided by h into divided by h cross into x. This is time dependent form, time dependent term. This is time independent term. So our statement says time dependent term doesn't affect us anymore. Only this time independent term is what influences the wave function psi. Right? We have split into time dependent and time independent.
Excuse me, sir.
Yes.
So once explain that step, sir. How did you split that?
Just split it. It is exponential, no?
Yes, sir.
Straight away split it. Minus into minus, this becomes plus. Here minus remains. E to the power of minus I e divided by h cross. T I have taken out. Okay. Into e to the power of minus I by h cross into px. That is minus into minus becomes plus ip by h cross into x. Not clear?
So I didn't understand how it does not depend on time anymore in the second equation, sir.
See, in the second equation, we have split the terms into time-dependent part, the part which has time, and the part which doesn't have time. That is only the position. Okay, we have split into two.
Okay, sir.
Okay, here in many cases, the potential energy of the particle depends only on the position. Time would not affect it at all. Such as, we have a nucleus, let's say hydrogen nucleus, that is a proton, and an electron revolving around it, and electron revolving around it, and electron revolving around it. Right? When an electron is here,
Yes.
it has some energy. Right? Throughout this orbit, it has same energy, right?
Yes, sir.
When an electron is here, it has different energy. When an electron is here, it has different energy. Now, the energy of the electron depends on what?
Orbit.
Distance from the nucleus.
Distance from the nucleus. That is the position. Can we say it is position?
Yes, sir.
That doesn't depend on the
In-
time, but it depends on the position of the particle, right?
Yes,
So
sir.
in this case, this part, wait, this part, which has time as variable, this part becomes a constant. Yes or no?
Okay.
Okay. Whereas this part, it keeps varying because x is the function or x varies. So this part becomes constant, whereas this part continues to be a variable.
Okay, sir.
Okay. So now, we'll rewrite this as all this A and this, A and this time part put together. Let us call it as a different symbol, psi. This is also, we call it as psi only, but it is a symbol is different. Slightly bend it. Sorry, wait. Sorry. Now our wave function is A into this part, whereas this part continues to be a constant. This part is a constant, whereas our wave function, or we define our wave based on A into e to the power of IP by h cross into x, because only these two constitutes this. Of course, it has to be there because it is amplitude which varies, and this is the varying part, whereas this part is a constant. So let us keep the constant as it is and rewrite the wave function only which constitutes of A into e to the power of IP by h cross into x, where P is equal to, we write like this, slightly slanted. P is equal to A into e to the power of IP by h cross into x. This is the equation.
Sir, there are two, no, sir. I into e power IE by h and IP by h. Those two combined are.
No. IE by h we are keeping as it is because it has become constant. It no longer influences the particle. Particle doesn't depend on time t, so it becomes constant. Particle depends on the position. Therefore, we will rewrite the particle's wave function as.
Sir, that is
Position
amplitude, no,
dependent.
sir.
Yeah, amplitude has to be there. So particle
sir.
wave function.
Sir, from second step to third step, how it came? Would you explain, sir?
I know this amplitude and e to the power of IP by h cross p, that I have rewritten as phi into e to the power of minus IE by h cross t. You didn't get this?
Sir,
one.
sir, sigma is a e power minus I by h et minus px, right, sir? So how you can write
Yes.
sigma there, sir? Only a e by ip by h is there.
Wait. So now you understood that. Let me come back. Give me a minute. Now you understood that one is time dependent form. So this time dependent form doesn't affect the particle, whereas this part affects the particle, right? Do you agree that
Yes,
this
sir.
part affects? Now we will rewrite this as a into e to the power of ipx by h cross into e to the power of minus ie t by h cross. Okay. This both put together, I will rewrite the wave function psi is equal to phi into e to the power of okay. Now this is the wave function which represents our particle. This is the wave function which represents our particle, or which constitutes the probability of the particle. Probability is the varying one, so that probability depends only on
Sir, the
phi.
circled one is different symbol, sir. It's not psi.
Yes, different, slightly slanted. This
Okay,
one,
sir. I thought it's
see,
psi.
this one is straight. No, you slant this
Okay,
slightly. Okay, you bend it by 30 or 40 degrees. Okay, so now.
So that means it's now a new constant, sir.
I did. Yeah, which one? Which one?
That slanted, slightly slanted one, sir.
This is not. This is the variable. This is the variable. This is the wave function now.
So that value equals to a into e power.
Yes, this value equals a into e to the power of ipx by h. So this is the wave function which represents the particle, that depends only on the position, or which represents the particle which is time independent. This represents the particle which is time independent. Okay. And we want to find the Schrodinger's equation in time independent form. So this represents time independent particle. Okay.
Okay, sir. Okay, sir.
Okay, we'll continue day after tomorrow. We'll stop here.
Sir, means now which is the equation, sir? Means this one, means the slanted
this full
one, or
equation is the equation. This full is the equation. We will continue with this equation only. This equation and this equation same.
Sir,
Yes.
sir, why are we considering I in every equation?
It's a complex quantity, right? Whenever we consider what is this wave equation, we get complex quantities. We can't help it.
Okay, so for
Wave
every
as complex
equation we
as
have
well
to
as
consider I.
see the wave complex quantity I means it represents real and imaginary part. Okay. So when we consider such quantities, the quantities are complex quantities. It may have real quantities as well as imaginary quantities. Just like what you studied in dielectric of materials, right? Like that,
Yes,
we have the real and imaginary parts. To represent real and imaginary parts, we need this I.
Oh, okay, sir. Thank you.
Okay. Here, wave function is also constitutes of real and imaginary parts. That I told, no, psi is equal to a plus psi b or a minus psi b. That is the imaginary part.
sir,
So it has
now
it is
the
in general complex. That is why. Yes.
sir, here the time independent is taken as this slant sign, no, sir.
Exactly. You are right.
That name what, sir? That's psi name.
You
It means
call that also as psi only, because later on we'll be going to use this only. We'll be using this only. We'll get rid of this. So don't worry. You call that also as psi only, but with a slanted representation. Okay.
Sir, also now today you told some derivations, all these things, no, sir. These all are necessary for exams, sir, because some are some complicated. That's why.
No, they are not complicated. They are